Section: Introduction. In this section, we discuss the importance of data quality in enhancing the performance of large-scale pre-training tasks. We have observed that training on well-organized datasets leads to better performance with less data in various domains like language, vision, and multimodal modeling. However, the current manual data curation process is challenging and costly to scale. On the other hand, model-based data curation, which leverages the model's features to select high-quality data, shows potential in improving the efficiency of large-scale pre-training across different modalities. Previous methods focused on curating individual data points, but we believe that the quality of a batch is influenced not only by its individual data points but also by how these points interact within the batch. For instance, in computer vision, clusters of points with different labels, hard negatives, have been found to be more beneficial for learning than easily solvable ones. Our goal is to explore whether applying model-based data selection criteria to batches of data can enhance learning beyond what is achievable by selecting examples independently. We introduce a simple and practical algorithm called JEST for joint example selection. JEST efficiently picks relevant subsets of data from larger batches based on their model-based scores. By scoring batches using a pre-trained reference model, JEST speeds up learning compared to uniform batch selection and even surpasses independent example selection methods like ClipScore. When batches are scored based on their learnability, considering the online model loss, JEST performs even better, matching the performance of top models with significantly fewer training iterations. Identifying highly learnable batches involves sifting through large amounts of raw data. We simplify this process by using recent advancements in online model approximation, which reduce computation while still providing accurate predictions. By training a single model at multiple resolutions simultaneously, we efficiently score large batches, identify the most learnable subsets, and allocate more computation resources to learning from them. This approach, called FlexiJEST, produces state-of-the-art models with fewer iterations and computational operations. A key aspect of our framework is steering the curation process towards datasets that resemble smaller, well-curated datasets. This is achieved through model-based selection criteria, where a pre-trained reference model guides the curation of a larger dataset, leading to improved model performance on various tasks. We also review related work in offline curation, online data curation, hard negative mining, and model approximation techniques. Our method stands out by enabling joint example selection tailored to accelerate contrastive pre-training objectives, offering a more efficient and effective approach to data curation for large-scale pre-training tasks. Section Summary. In this section, we explore the concept of model-based data curation for large-scale pre-training across different modalities. We introduce JEST, a method that efficiently selects relevant sub-batches of data from larger superbatches based on model-based scores, accelerating learning compared to uniform batch selection. By leveraging online model approximation techniques, FlexiJEST significantly reduces computation overhead while maintaining training efficiency, leading to state-of-the-art models with fewer iterations and flops. Section: Methods. In this section, we will discuss our model-based batch selection criteria. We consider the learner model that we want to train. When we have a large set of examples called a superbatch, D, we aim to choose a smaller subset, B, from it that is most relevant for learning. Instead of scoring individual examples and sampling based on those scores, we score entire subbatches and sample according to these batch-level scores. One approach is to prioritize batches with high loss under the learner model, discarding trivial data. Another approach is to upsample data that is easy, has low loss, for a pre-trained reference model. We can also combine these scores by prioritizing based on the difference of losses, which helps in upsampling data that is both unlearned and learnable. The ratio of the subset batch size to the superbatch size determines the filtering ratio, which is the proportion of data discarded at each iteration. Higher filtering ratios increase the scoring cost as they require more passes on the superbatch. For multimodal learning, we use contrastive learning to align paired images and text while minimizing the alignment of unpaired examples. The batch level loss is computed using a contrast function, and we show that the sigmoid contrastive loss is a more scalable option. We aim to sample batches based on their joint learnability, which decomposes into conditional learnabilities of individual examples given other examples in the batch. We use a sequential approach inspired by blocked Gibbs sampling to sample batches in proportion to their joint learnability. We iterate through chunks of examples, sampling new chunks independently based on their conditional learnabilities. The batch is updated by adding these chunks iteratively until a certain number of iterations is reached. The first chunk is sampled based on unconditional learnability, considering only self-similarity. We find that a small number of chunks is sufficient to create batches with high learnability. Section Summary. Methods. Model-based batch selection criteria are proposed to extract a maximally relevant sub-batch for learning by scoring entire sub-batches and sampling based on these batch-level scores. The learnability scoring heuristic combines prioritizing high-loss batches under the learner model with up-sampling easy data for a pre-trained reference model, showing effectiveness in accelerating large-scale learning. Joint example selection for multimodal learning involves sampling batches in proportion to their joint learnability, achieved through a sequential approach inspired by blocked Gibbs sampling. Section. Efficient scoring and multi-resolution training. In this section, we efficiently score large super batches by using online model approximation to reduce the cost per iteration. We adopt the flexi-vit architecture to lower image resolution while maintaining performance. By evaluating super batches with 32 by 32 pixel patches, we achieve significant reductions in flops and wall clock time compared to full-resolution scoring with 16 by 16 patches. We also implement multi-resolution training to score examples at low resolution during training and at full resolution during testing. This involves training at both resolutions by splitting the batch into halves and encoding each half at a different resolution. Multi-resolution training not only enables efficient scoring but also leads to efficiency gains during training. Furthermore, we use joint example selection, JEST, to select highly learnable batches during training. JEST algorithm efficiently samples submatrices of examples based on their learnability, accelerating multimodal learning. By training on more learnable batches selected by JEST, we observe accelerated learning and improved final performance on downstream tasks. Overall, our approach of efficient scoring, multi-resolution training, and joint example selection significantly enhances the training process and boosts performance on multimodal learning tasks. Section Summary. In this section, we efficiently score large super batches by using online model approximation, which reduces the cost per iteration and enhances efficiency gains. We adopt the flexi-vit architecture for multi-resolution training, allowing us to train at both low and full resolutions, resulting in a significant reduction in flops and wall clock time. Additionally, our joint example selection, JEST, algorithm effectively accelerates multimodal learning by selecting highly learnable batches during training, leading to substantial performance gains in downstream tasks. Section. Synergies between multi-resolution training and online batch selection. In this section, we explore the synergies between multi-resolution training and online batch selection. We find that joint example selection with learnability scores can be more efficient when larger fractions of each batch are filtered. However, the cost of scoring leads to a significant increase in computational overhead. For instance, filtering 80% of the super batch results in 4 times more computational operations per iteration compared to IID training. To address this issue, we introduce FlexiJEST, a compute-efficient variant that utilizes multi-resolution training and low-resolution scoring to reduce the total overhead to only 10% compared to the baseline. When comparing FlexiJEST to JEST, we observe a decrease in per-iteration performance, but it still offers significant speedups over IID training. Notably, our best FlexiJEST model achieves the same average performance as a 40B SIGLIP run with much fewer computational operations. By varying the fraction of data trained at full and low resolution in FlexiJEST, we ensure that the learner spends the same computational resources. FlexiGest outperforms the multi-resolution baseline as long as the low-res model trains on enough data to align with the learner. We also investigate different curation strategies for Jest performance, ranging from weak to strong curation levels. Surprisingly, we find that the performance of the reference models and Jest training are not strongly correlated, indicating that increasing curation levels may not always lead to better models. By scaling data curation, we observe a clear correlation between improved reference models and better Jest pretraining. This suggests that Jest could benefit from further scaling of data curation for the reference datasets. To address this, we expand the WebLI curated dataset to include more examples sourced from a wider range of image-text pairs. This scaled dataset, named WebLI Curated++, significantly improves both reference model and Jest performance. We find that pre-training on the original WebLI dataset is still necessary, as it helps in achieving a generalist foundation model that outperforms the baseline on various benchmarks. Section Summary. In this section, we explore the synergies between multi-resolution training and online batch selection. We find that FlexiGest, a compute-efficient variant, balances training and compute efficiency by using low-resolution scoring and multi-resolution training. By varying the fraction of data trained at full and low resolution, we show that FlexiGest outperforms the multi-resolution baseline when the low-res model trains on enough data to align with the learner. Section: Comparison to prior art. In this section, we compare our approach to previous methods, such as the SIG-LIP model and other CLIP variants. Our model, Jest++, outperforms these existing models by achieving a new state-of-the-art on ImageNet and COCO datasets while using significantly fewer training iterations and less computational resources. Specifically, Jest++ improves the previous best results by over 5% on COCO and surpasses the state-of-the-art even when using 10 times fewer iterations and 4 times less compute. Another variant, FlexiGest++, also exceeds the previous best results on average while using 9 times less compute. When we trained Jest for a longer period, we observed further improvements in performance. Our results also show that the effectiveness of our approach scales well with the size of the model. Even when using a smaller dataset, Jest++ demonstrates accelerated learning comparable to the SIG-LIP model trained on a much larger dataset. We also applied Jest++ for pre-training on the LAION2B dataset, surpassing previous methods in offline data curation efficiency by using 4 times fewer training examples. Our experiments indicate that Jest outperforms other methods, including SIG-LIP, even with a limited training budget. The dataset we used for pre-training, WebLI, was already filtered for high image-text alignment, which is crucial for effective training. Interestingly, Jest++ does not show performance degradation when trained on the unfiltered WebLI dataset, eliminating the need for pre-filtering foundation datasets. In summary, our method, Jest, significantly accelerates large-scale multimodal learning by selecting the most learnable data batches. It outperforms previous methods by up to 10 times in terms of computational efficiency and requires 13 times fewer examples. Our findings suggest the potential for improving pre-training efficiency by using small curated datasets to guide learning on larger uncurated datasets. While our approach has shown promising results, it relies on well-curated reference datasets. Future research could explore methods for inferring reference datasets from downstream tasks to further enhance the effectiveness of our approach.